Good evening, everyone. This is Douaa Amina from Cassiopeia team, and today we're going to talk about astronomical image processing. So, in this first part of our image processing course, we'll dive into the fundamental building blocks of digital images, pixels. A pixel short of picture element is the smallest individual point in a digital image or on a display screen. Think of it as a tiny colored square. Each pixel holds a specific value that determines its color and brightness. As you can see here, a picture of element or pixel. This is a picture element or a pixel, and this is an addressable point. Now let's go explore the types of images. Starting with the grayscale image. In a grayscale image, each pixel's value represents its intensity or shade of gray, ranging from pure black to pure white. These values are often represented by bits. Yes, bits like in the binary system. So each bit might take either 0 or 1. These are possibilities. Imagine that this square is a bit. So it might take 1, this one. So it might take 1 or 0 as values, of course. So it's gonna be like 2 power 1. And the same for 2 squares, 3 squares. So here we deal with 8 bits. Eight bits refers to or gives us 2 power 8, which results to 256. And this is the set of possibilities of shades of gray and or gray from white to black, from black to white colors that might take this pixel. So we said that each pixel's value represents its intensity or shade of gray, ranging from pure black to pure white. These values are often represented by bits. For example, an 8-bit grayscale image means each pixel can take on 2 power 8 or 256 different intensity levels, typically from 0 that indicates black to 255 that indicates white. But when we're dealing with the image, the values vary from 0 to 255. And since it's starting from 0, so 0 is counted. The set of possibilities would be 256. The highest value would be 255, since we are starting from 0. So the higher the bit depth, the more shades of gray are available, resulting in a smoother transition between tones. Now, contrast this with RGB, red, green, blue, the second type of images that we're dealing with. RGB images are widely used and represent color by combining varying intensities of red, green, and blue light. Each pixel in an RGB image has 3 separate channels, one for red, one for green, and one for blue. Each of these channels typically has its own 8-bit value, allowing for an incredibly vast range of 256 times 256 times 256. So it's more like 2 power 8. All right, this is a 8. The all of it is power 3, or over 16 million possible colors for each pixel. Now you might wonder, why do we sometimes use grayscale images instead of full color RGB images, especially in specific applications like asteroid detection or asteroid research, like we used to do in um, the activity of asteroid research with Isaac? The primary reason is efficiency. Grayscale images are significantly smaller in file size compared to their RGB counterparts, because they only need to store one value per pixel instead of three. This reduced data size makes processing much faster. Furthermore, for tasks such as detecting moving objects like asteroids, the color information is often irrelevant. What matters most is the change in brightness or intensity of objects against our background over time. Using grayscale images simplifies the data, making it easier and quicker for our algorithms to identify subtle movements and anomalies without being burned by unnecessary color data. This streamlined approach allows for more efficient and precise identification of celestial bodies.